Welcome to the last part in this 3D vectors course, and we're looking at intersections of planes, and we're asking the question, how do you tell whether they're going to intersect and what that intersection is going to be like? Well, have a look around the screen. Oh no, look up here. I wish these guys would learn that this is math space, not airspace, and get out of there. Anyway, not to worry, let's have a look around the screen now and have a look at some scenarios where flat surfaces can intersect either pairwise, not at all, parallel planes. Oh, here's an interesting one. They're intersecting right in a single point there. That's what we would call a unique solution. Okay, so you might have done some of this sort of work with 3x3 systems in another course. But what we're going to do here is look at a 3x3 system where X, Y, and Z are the coordinates in a three-dimensional situation and represent a plane. So look at these. They all intersect pairwise. Oh, these intersect in a line. That might be an example of infinite solutions where they all share the same line. So when you're trying to find the point of intersection, there's going to be an infinite number there. And over here, we've got also a line. We've got two planes that are equal to each other. They're coincident. They are the same plane. So what we're going to do is try to find the intersection of planes by putting all their equations together and solving them as a set. Okay, let's come down and have a look at some of this stuff. Here are the scenarios that are possible. Let's look at two planes. They could intersect in a line. So our job here, just remember, our job in finding the intersection would be to find common points in the plane. Okay, so we want common points, and in 2D land we put the two y expressions equal, don't we? That could be more difficult here because we have x plus y plus z equals 10, and maybe 2x take y plus 3z equals 15, that sort of stuff. So the intersection here is going to be more difficult with three coordinates here, or three variables, okay, because the plane is a flat surface in 3D space and is described by those things. So how are you going to find where these two, or maybe even a third, have something in common? Okay, well, let's have a look at this one. This is parallel and coincident. They're the same plane. Okay, now I think we can pretty well tell parallelism now, can't we? We have to have the same direction of the normal to the plane, and that would mean that the ratio of those would be the same in the two planes. Of course, this is not the case here. This one has a normal which is 1, 1, 1, and this has a normal 2, neg 1, 3. So parallelism is going to be fairly easily detected. So should coincident, because coincident means when you, if you like, simplify or divide both sides by a number, you'll get the same equation. Okay, something like 2x plus y plus z would become 3x plus 3y plus 3z equals 30. That would actually be the same plane, wouldn't it? Multiplying both sides by a constant there. So these scenarios aren't too bad in the case of two planes. Let's go and have a look at the case of three planes. Okay, well, they could all be the same plane. They all cancel down to the same expression, if you like. Two coincident, so two planes are actually, when you look at their equations and divide both sides by a constant, come to the same thing, and then cross by another. Okay, so here you would have infinite number of shared points. They are the same plane. Here's there's an infinite number of shared points, all the points on that line. And then two coincident and one parallel. These two would be the same plane, and this one would be separate, and they're parallel, so there'd be no common points, so there'd be no solutions when we're trying to find the points of intersection. All meet at the one point. We've already talked about that. That'd be a unique possible solution there. All three parallel, no solutions there. no common points of intersection. And here 2 parallel and 1 other. Okay, so here we've got this one and this one sharing points, an infinite number of points, and this one and this one. But all 3 together don't share any points altogether. So there'd be no solutions there. All meet in a common line. Well, the points on that line, infinite number, so there'd be an infinite number of solutions there, shared by the 3 planes. And then the last one would be no solutions either, because you'd have, maybe 3 possible lines of intersection, but none of those points are shared by all 3 planes, so there'd be no common intersection points there. Okay, so you should be aware of this. In this particular course, we don't do a lot of work with this because it's covered in another course, solution of linear equations in 3x3 systems. So you should know what's going on here, but it's not a big focus. So be aware of what's happening as we look at some exercises. All right, come down and let's have a review of what's been done in other courses. So we're looking at the solution of a 3x3 system here, 3 equations in 3 unknowns, and we're trying to find a solution which is values or points or lines, x, y, z's, that satisfy all 3 equations. So we're trying to solve these simultaneously, and it's very much like back in your junior maths where you were solving 2x2s by elimination, trying to eliminate the x or y value and then get the other one and sub it back into the other equation. Do you remember that stuff? So we're going to use row operations. We're going to first of all summarise this system as an augmented matrix. This is just a summary of what you might have done before. Augmented matrix, so we're just detaching all the coefficients and the constants on the right there, and just remembering what that augmented matrix means. And then what we're going to try and do is do a process of elimination with row operations and combining equations so that we get this. And this is called the row reduced echelon form in technical terms, a row reduced echelon form. Okay, and that's handy because see what we've got? We've only got the z coefficient and an answer here. So we would read this bottom line, we're going to talk about this extensively in a minute, as 0x plus 0y plus, we should have a y, how we do that, plus hz equals I. Okay, so what that means is these come to 0 and z is I over h. And then if we can get an answer, we can substitute the z back in here and get y, and then y and z back in here and get x. So it's an extensive elimination process and back substitution, if you like. So this is our goal, to create this little triangle down here with zeros so that we can have a final equation in just one unknown and then substitute it back. So that's a little bit of a review. If you haven't done that in another course, you might have a look at the problems down below and have a go there in a minute. All right, let's have a look at what happens now when we do get that row reduced echelon form. And I want to make it very clear again that this bottom row, this is the problem with matrices. They are arrays of numbers and they have multiple uses. Okay, so when you create an augmented matrix, never forget what it's about. Okay, where those numbers came from, because each array like this means something different. Like if you're doing other courses, this top line would mean ax plus by plus cz equals d, sure, but x, y and z might not be the displacements on a 3D plane. They might be the number of tennis balls, soccer balls, cricket balls in a sports store or something. Okay, so the variables here we are talking about, in our context, where we're talking about 3D vectors, and therefore that is the equation of a plane there. Okay, so everything's got to be taken in context. Be careful. So let's write this bottom line out. Naught x plus naught y plus hz equals I, which implies z equals I over h. Now what we want to do is to discuss what's going to happen there for different i's and h's. So first of all, you can see h should not be naught. Come over here. If h is not naught, we can determine that uniquely, even if I is naught, because here it would be z equals some number, even naught, over h. That would be okay, but you can't have this one as 0 because dividing by 0 is undefined. So there would be a unique solution, and we're going to see that in a couple of examples coming up in a minute. Now, if h equals naught, we're in trouble, because if h equals naught, we've got this bottom row, and let's say I is not equal to naught. Okay, I is not equal to naught, so that's still a number. And so the bottom row, just remember what it means, naught x plus naught y plus naught z equals a number. Now this is impossible. We call the system inconsistent. All right? That line, that bottom equation is not consistent with a solution. Okay, so there is no possible values here because the set of equations is inconsistent. Doesn't work out, if you like. There's no x, y and z that can satisfy this. Therefore, there's no solution. Now, what if both of them are naught down here? Let's write it out again. Naught, 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 naught. This is naught x plus naught y plus naught z equals naught. Well, what can you say about that? Well, that's always true. Okay, that's always true. X, y and z could be anything, and that would still work. So what we've got here is basically the demise of that last equation. X, y and z could be anything. So effectively we're still left with the constraints of row 1 and row 2. Okay, they come up here. We still, if this goes to all zeros, still have some information about a possible solution, because there's actually an infinite number. Come down here again, down the bottom, there's an infinite number of z values you could start with and create x and y's related to it from the top 2 rows. So the book here is calling this a free parameter. Remember, a parameter is another variable within the system. And so here we're saying what was the variable? The freedom of specifying any z. You could let x be t actually, but we do it like this because we're starting down at the bottom and saying if we've done our row reduced echelon matrix, we come with hz equals I and z equals I over h. So then we're going to back substitute. So let's say z could be anything. That's our free parameter, if you like. So here the parameter means that all the possible values of z in this context, so it's free. Okay, for example, by letting z equals t now, we can write x and y in terms of t, and the free parameter can take any real value. So we usually write t as a member of R there. Okay, so you back substitute, you take your possible value of z here, go in there and get y in terms of z, and then take the z and the y in terms of t and go to x. So that's the idea now. All right, so let's have a look at one. And again, these screen clippings are taken from Hayes and Harris. So this is from another course on math studies. So let's have a look. We've got a system here, and in this system, what we're saying is x, y and z are coordinates or represent displacements on a 3D plane. Okay, on a 3D system. Okay, So in augmented matrix form, we just attach the coefficients 1, 3 and -1, 15. So it goes there and so on. So now we're ready and we say this is equivalent to, that matrix is equivalent to. Now what are we allowed to do? Systems of equations, so we can multiply whole rows by anything. We can add and subtract rows, just keeping in what mean here from the rows within this matrix. And so we could multiply the first one and add the second, just like we've discussed in junior maths with 2x2 systems. All right, so let's see if we can create a 0 here first, and then we'll try a 0 here. In this example, the book has done 2 operations at once. I suggest you only do one. Try to create that, and you'll create that by saying, here, let row 2 go to row 2, take to row 1. Okay, so here we are. There's row 2, and minus 2 row 1, and we've been able to create a 0 there. I strongly recommend that you write this out, both for part marks, but also to avoid making an error. Matrix row operations is notorious for people making arithmetic errors with negatives and things, okay? So just keep in mind we're subtracting the whole row, so that's going to be written like that then, okay? So 2 row 1, looking at that, minus 2, minus 6, minus -2 is plus 2. So that's the problem here. You've got to watch the signs here. Okay, so now we've created that 0, so we'll put that row in. There it is. And you must put what you've done here, even if you don't show the working over here. All right, so now let's do this 0. Create that 0 there. Now, how have we done it here? You must work with these 2 rows. Here, row 3, we need to work with that. Oh, hang on, we're up here, sorry, because we're doing 2 at once. So work with this one, row 3, and just take away row 1. Okay, we'll give you a 0 in that position. All right, so here it is over here. Row 3, take row 1. We're saying our new row 3 is row 3, our old row 3, take row 1. And put it carefully there. Taking row 1 is take 1, take 3. Take -1 is plus 1, take 15. Okay, so you could write it out like that. Okay, another way of doing it, of course, is to do it like this. Come over here, 1, 3, -1, 15, and 2, 1, 1, 7. Okay, so here, oops, we used the wrong one here. So we want row 3, we'll put this up. That's row 1. Row 3 is this one, and 0. So if we had row 3 minus row 1, you could put it like this to avoid confusion. 1 take 1 is 0, -1 take 3 is -4, -2 plus 1 is -1, 0 take 15. If you want to do it that way rather than changing the signs over here. All right, okay, so we've got those 2 zeros. Now we are locked in, aren't we? We don't want to mess these zeros up, so we can no longer use row 1. If we start to add and subtract that from this bottom row where we want this 0, then it's going to mess up the 0 we already have. So we've got to combine this row 3 with row 2, and this is fairly difficult here, because looking at this, we want these 2 to be the same, so you can subtract them. So this is a common denominator idea. So if you multiply the -4 by 5 and the -5 by 4, then you're going to get that common number there of 20, and then you can subtract them if you like. Okay, so here, what are we doing? 5 times row 3 is -20, 5, -5 and -75, and then 4 row 2 is 0, -20, 12 and 92, but taking it away it becomes 20, -12 and 92. Okay, so we're going to subtract those. So this is the idea of a common denominator. They're nowhere near, up here they're nowhere near equal to each other, so multiply one by the other as you would with a common denominator and additional fractions. So now, what have we done? Well, we can see here, we can talk about this, and what does that mean? Remember, it means 0y plus 0z, 0x plus 0y takes 17z equals 17. So z is 17 over negative 17, neg 1. Now, we can go back to row 2, and row 2 says that, and stick in neg 1 in place of z. So 3 times neg 1 is neg 3, and we come on down here a little bit, and we can solve this. Okay, so then neg 5y equals neg 20y is 4. Now go back into the original equation, which is still intact in row 1, and put in the values for y and z that we've found and get x is 2. So we've got a unique solution there, 2, 4 and neg 1. All right, well, what does that look like? I think that's pretty good. You can actually do it on a calculator, and this is the TI, the Casio doing this, probably best done in equa mode, not in matrix mode there. Equa mode, simultaneous, and 3 unknowns, and just enter the 3 linear equations in there. Alright, so you need to have this sort of skill with row operations, not examined as such in this course, but the interpretation is very important, so you should be able to do it. Alright, let's have a look at some exercises now. So it's important to try and, I think, sketch a situation which is going on. If you're talking about parallel and coincident, and just get a picture of what that would look like, and go back to the original little sketches at the beginning of this presentation, or in the textbook. Alright, so pause it for question 1 and 2. I'm going to go through each of them and then show you the solutions. Let's go to 3, 4 and 5. Okay, you might try a couple of these to check you can do row operations, and the important thing in this part, this course, is not so much that, but it's interpreting what the result is at the end, what is actually happening, to be able to describe in 3D space what's happening with these planes. Right, come down and let's look at the last one, question 6. So these are interesting questions because they've got unknowns here. Okay, so you need to check that out and discuss all possibilities. And again, an interpretation about if x, y and z are coordinates on Earth in 3D space, then what does this mean about the planes, interpreting it in that context particularly. So it won't do to say it's got unique solutions or infinite solutions. That's got to be interpreted. All right, come on and let's have a look at the solutions now. Well, the boat's rocking a bit there, gone off to the side. So there's question 1 down to part 3. Okay, question part 4, there's part 4 and sum of 2. I'll bring 2 up in a minute. Okay, there's question 2. And let's go on to question 3. Can we fit 3 and 4? No, we've got 3 and 4 part A. And then part B and C, see if we can get those on there. No, just B. Okay, and then C and D. And then in E and F. And then question 5 and part of 6. and question 6. Fair bit of hard work there. And the last part of question 6. So congratulations on making it through to the end of this course, all 7 parts, and in 3D vector land. And I hope you see how neat vectors are in doing geometry in 3D space. So there are more instalments here in this course, so I look forward to catching up with you a bit later on. Cheers for now.